In this video, I'm going to talk about this GNURadio script, and it's used for the ARRL frequency measurement test, which is a test done a couple times a year in November and April, where someone will broadcast a frequency or a tone for about 2 minutes on 20, 40, 80, and 160 meters. And very precise, coming off the source, which has been synced to a GPS disciplined oscillator. So people around the country or world will try to measure this tone and see how accurately they can measure it over that 2-minute period. I'm using a all SDR approach. I'm using an Ettus USRP X310, and that's a 200 megasample per second SDR with a 10 gigabit Ethernet output into the computer. The SDR has a GPS disciplined oscillator, which has the Allen variance over 1 minute of 1 times 10 to the negative 11th. And what that means is if I were measuring a 10 megahertz signal over a minute, the variance in frequency is going to be about no more than 100 microhertz. So I should be able to get very precise frequency measurements in the HF band. This Ettus X310 is equipped with 2 daughter cards. The first daughter card I have is the WBX, but the one I'm using for this is the LFRX. There's also an LFTX, but the LFRX board is actually DC coupled, so can go down to DC and VLF and all that good stuff, and runs at 200 megasamples per second, the analog digital converter in there at 14 bits, I believe. So it's going to be doing direct sampling, and in that, once it does the direct sampling, we're going to decimate it down and spit it out over the Ethernet into the GNURadio script right here. Alright, my receive chain actually starts out in the yard. I've got a PixelSat RF1 Pro B active loop antenna. That's about 1 meter in diameter. And it's a active magnetic loop, which the nice thing about using that for receive is it's got 2 sharp nulls perpendicular to the plane of the loop, so it's very good for knocking out terrestrial noise sources like the big power transformer in my backyard and other stuff. But skywaves coming down, it doesn't null those out because there's no nulls coming out the plane of the loop in the top. Anyway, so that active loop feeds into a AM band reject filter, and that's used to knock out, we have several strong AM stations in this area, and that will help reduce any intermod problems in my A to D in the USRP and allow me to increase the gain on the thing. So starting with the GNURadio block right here, we'll start with the USRP source. I set my address. I've got a 2 Ethernet cards in this computer, and one of them is a 10 gig E connection that will handle the full 200 megasamples per second from the USRP. And I've actually been able to do 200 megasample per second complex FFTs. I could actually feed it into GQRX, but I couldn't demodulate anything. Knocking it down to 100 megasamples per second, I was able to demodulate a narrowband FM channel. So pretty impressive what you can get these days in the real-time bandwidth. Anyway, you set the address here. And right here is a subdevice spec. This B:(A) means daughter board B, and then device A on that daughter board. And device A is going to be the first channel of the LFRX card, which is hooked to the antenna via the AM band reject filter. If I were to specify B:(AB), that would select both channels, sort of like an oscilloscope, except not interested in that one channel. So since we're doing direct sampling at 200 megasamples per second of channel A. And a sample rate is actually set right here by the variable. It's 250 kilosamples per second. So the USRP is taken in at 200 megasamples per second. Within the FPGA, it's doing decimation down to 250,000. That's the lowest it can go, and that's appropriate for HF reception since the amateur bands don't tend to be larger than 250 kilohertz. And then I'm setting the center frequency. So the signal comes in the LFRX card, and it's DC coupled and goes into the A to D and then into the FPGA. So it's sampling real sampling. It's not doing a analog IQ down conversion first and pulling in I and Q signals into the A to D. Just all real sampling. So what happens if you set a 0 hertz center frequency into the USRP, into its digital down converter, it will give you true real sampling out. You'll get a signal out on the I or the channel 1. You won't get anything on the channel 2, which would normally be the Q channel. But if you set it to a tuning frequency, it will start a digital down conversion process where it takes those real samples and multiplies them by a complex sinusoid, and it will spit out a complex spectrum then at 250 kilosamples per second in width, and then we'll further process that complex spectrum to decimate it down further and filter it. And then I've got this channel gain right here, which is actually just gain within the FPGA. It's a digital gain. Now, I begin my the tuning process. We need to choose the center frequency to tune the USRP to. So I've got this GUI, Qt GUI checkbox, chooser box right here. So I set three different frequencies for band centers for the 60, 80, and 40 meter bands. And notice I also have 2.5, 5, and 10 megahertz, and that's for checking WWVB, the AM carrier on that, as a figure of merit, so to say. So we're going to take these, and this is called band frequency right here. And now you notice I also have an offset tune of minus 10 kilohertz. The output of the DDC out of the USRP in GNURadio, again, it's 250 kilohertz decimated band. It's minus 125 to plus 125 kilohertz. And we're offset tuning, so there should be no DC in this thing. And no gain in DC imbalance, which would cause bleed through in a normal complex sampling out of an analog IQ down converter. So it's offset tuning, but I'm still seeing a little bit of spike, little signal at 0 hertz, center of the decimated band. And I believe what may be causing that is it could be since the FPGA is using fixed point arithmetic versus floating point. It could be that. It could also be in the digital down converter. There's either probably a Cordic algorithm in there, but what I've also read is that the lookup table used to generate the sinusoid within the FPGA, it's 32 bits precision is what you're using, but you can't have a full 32-bit length lookup table. That's a huge amount of RAM. So they truncate that down to a finite length table, and that's going to cause spurs in your spectrum, and maybe it's coming from that, I'm not sure, but I want to tune around that, so I'm going to tell the thing not to tune to the center frequency I call out in the checkbox, but tune 10 kilohertz lower, and 10 kilohertz is outside my final decimated bandwidth that I'm going to record to disk, which is 2500 samples per second. Now up at the top here I've got these two import blocks. This first one imports numpy as a shorthand NP. Now what this block is doing is in the Python script that GNURadio Companion generates, the top-black.py, it's going to install this at the this import at the top of the script, so we can use this numpy function in the block diagram here. I'm also going to use do the same thing with time, because I'm going to use this to timestamp the files that it saves. Now, the USRP has the numerical oscillators in the USRP's digital down converter. It has a finite tuning precision of 32 bits. Think of it as a 32-bit NCO. So when I ask the USRP to say tune to 10 megahertz, it's not going to exactly tune at 10 megahertz. The UHD library that controls the USRP will return the frequency that it's tuning to, but it's only got 1 hertz resolution in that return frequency, and we need to go smaller than that. I want to get down to microhertz. So what I can do is pre-calculate that so I know what it's tuning to, even though it doesn't tell me what it's going to tune to. So I take this frequency right here, that frequency I'm going to ask the USRP to tune to, which is the band frequency from the Qt GUI chooser, and then the 10 kilohertz negative offset. That's what it tunes to. Then I'm going to calculate the actual true digital down converter frequency, and the way I do this is I'm going to take the frequency that I asked it to tune to and divide that by the clock rate, which is going to be 200 megahertz, and that's going to be the frequency. But then I'm going to multiply by 2 to the 30 seconds. It's just a 32-bit phase accumulator, and round that to an integer using numpy's round function. Then I take that and divide that value by 2 to the 32nd, and again multiply it by the clock rate of 200 megahertz. And that's going to give me a floating point value with the exact tuning. And you can see the value is right here, 7 megahertz, 7044999.9993. So you can see it gets to within, what is that, 70 microhertz of the true 7055 kilohertz. Right, the output of my USRP is going to be 250,000 complex samples per second. So I'm going to run that into a low-pass filter, and the reason why is that the USRP decimator uses a CIC filtering, cascade integrated comb, and it works, but I want to have it a little bit tighter. The problem is that signals that are just outside the band edge tend to bleed over into the negative frequencies, and likewise ones below it bleed into the positive frequencies of my decimated band. So I want to do a little bit tighter filtering. So looking at this filter, sample rate again is my system-wide sampling rate of 250,000. And the cutoff frequency I'm going to set to 100,000, and this is a low-pass filter, but you're filtering a complex signal. So what this will do is put a cutoff at plus 100,000 hertz and minus 100,000 hertz, and then the transition bandwidth goes 20 kilohertz above that, which just leaves me 5 kilohertz outside that. So if you can add that 120 and then the extra 5, it gives me the full sample rate. So the signal is going to be signals outside that 120 kilohertz band are going to be very attenuated, and we'll get much better rejection from close-in signals. My filtered output from the low-pass filter is going to go into a frequency translating FIR filter. What this does, it's equivalent of a decimator, but before that it's got a complex sinusoid source and a complex multiplier, so it's going to tune that decimator within that and filter within that 250 kilohertz bandwidth to give me a decimated signal out that's running at 25,000 samples per second. But before I go into this, I want to talk about the actual tuning of this thing and how we do that. So over here I'm going to generate a local oscillator value. I have two QT GUI boxes right here. One's going to be a coarse tuner, which I'm going to tune from minus 125,000 to plus 125,000 in 100 hertz steps. And it's, you can see it's sample rate by half, negative sample rate by half to the other upper end of the sample rate by half. And for the fine tuner value, I'm going to go just in 500 hertz values, minus 500 plus 500 in 1 hertz steps. So to actually generate the LO frequency, and this is extremely important because I need to know what the LO is running at when I do my post-processing, and it needs to be a very exact value. So I take my USRP DDC frequency, which is down to the, accurate to the microhertz level, and then I add that coarse tuner and the fine tuner, and then I subtract off the offset tuning value, which is 10 kilohertz. And this value is going to be written to the file, is actually going to be part of the file name, so I know what it is and I don't lose it. And then the value is also going to be fed up here to the frequency translating FIR filter. Now down here, I want to actually also create a label to show me what the thing is at. And I do this by just taking that and that value. Here you can see the LO frequency, and I've used Python formatting function to display that in a QT GUI label, and I want to do it to 6 decimal places of precision, again the microhertz range. Right, the output of my low-pass filter, I also want to display a spectrum of that 250 kilohertz just so I can see what's going on in the band, and I set the center frequency to the USRP DDC frequency, and then the sample rate of course is 250,000, and then scale the X and Y axis. Anyway, the frequency translating FIR filter, I'm going to do a decimation of 10, so that's going to get me down from 250 kilosamples per second to 25 kilosamples per second. And the center frequency, I'm using the LO frequency that I calculated down here, and then I'm subtracting the USRP's DDC frequency, and the reason I'm doing that is because I want to be able to show this as a 0 hertz center right here. And then I've got again the sample rate It needs to know that to do the proper scaling. So the filter caps, which I've defined right here, it's a low-pass design function from the FERDES library in GNURadio. These are normalized values, so this 2.5 is actually going to be 250,000, and this 0.1 cutoff is going to be a 10 kilohertz cutoff with a 2 kilohertz transition. So the 10 kilohertz plus the 2 kilohertz gives me 12 kilohertz, and that means I have 500 hertz left over that's going to get filtered, because you know half of that should be half of your, or that should add up to twice of that should be 25 kilosamples per second. The reason why I did these normalized values is because I'm going to use this same filter design in the next estimator, which appears right here. So back to the LO. If you look at this thing, I'm defaulting to 7.055 megahertz. Now I tune 10 kilohertz down, so that gets me to 7.045. Then I calculate the true DDC frequency, and these tuners are now defaulting to 0. So you can see that the actual frequency I'm going to be at is this value right here. So I'm down, what is that, 75 microhertz from the true frequency of right there. So then again, put that up into here and offset it so it shows up as 0 on there. Now the output of this decimator is now 25,000 samples per second. I'm going to decimate it by 10 again down to 2,500 samples per second, and that's a decent, typical sideband bandwidth for HF and audio frequency bandwidth too. All right, now that I have my audio frequency, band of 2,500 samples per second, I want to write that to a frequency sync so I can see it in real time. And I'm going to name this thing, of course, sample rate, this time divided by 100. So that's going to give me a string of value 2,500, and then concatenate that with this string right here. So in essence, it's going to say 2,500 hertz channel spectrum. And my bandwidth again is 1/100th of that was coming out of USRP, and I'll scale it again. Now I also want to record all this to file. I want to record that wideband just in case I miss something or can't find it. Could be below the noise in a 2,500 hertz bandwidth, and I want to do some post-processing later. So this file sync is going to write it to a file called file name. Now that file name, first we're going to have to define the name that we actually want to name it. So I've got this thing called file name string. And this is kind of a lengthy thing right here, but in essence what it does is take and take the time in UTC, Unix time in seconds in UTC. I'm going to take and convert that to an integer, strip off the floating point, then concatenate that with the letters UTC. Then I'm also going to concatenate that with the LO frequency down to the microhertz resolution again, kind of like I did in the GUI label that I displayed. Concatenate that with hertz. Then also concatenate it with the final sample rate, which is going to be 2,500, and then concatenate it with samples per second and the .raw extension. So this big long thing, the easy way to do this is to open up a Python interpreter, and you can type this thing in there and figure out how to get it to work correctly, and when it does work correctly, take and paste it into here. Now, this file sync is actually always writing. It's either writing to the file or it's writing to dev/null, and that's depending on this checkbox which I have right here. So the QT-GUI checkbox is called record checkbox, and it'll either be false or true. So when I check and want to record something, it will turn into a true. And I'm also going to display the label, this file name that I just figured out down here, so I can know what it's actually going to be called. Now the logic that decides whether it's going to be writing to dev null or the file name is down here. So my file name is actually going to be determined by this if statement right here. So if the record checkbox is true, it's going to be called file name string, which I determined right here. If the record checkbox is false, it's going to be /dev null. So I change that checkbox. Either it takes that calculation down here and sticks it into there, so I can toggle that in real time on and off when I want to record something. All right, now that I'm able to record it to file, I actually want to be able to hear what's going on. So I take that 2,500 samples per second. I'm going to low pass filter that to get rid of some of the noise. Before that, I want to show how I choose the bandwidth. So I've got this Q2E GUI chooser, and I can choose between 3 bandwidths of 100 Hertz, 500 Hertz, and 1 kilohertz just by choosing from this combo box. So I go into this low pass filter, no decimation on this thing, and a gain of 1. So its sample rate is again 2,500 samples per second. Now the cutoff frequency, I want it to be 90% of this CW filter bandwidth, and I want the transition to be 10% of that. Now, so you've got this filtered signal, which goes down to 100 Hertz, centered around 0 Hertz complex baseband. So I want to be able to hear that, because right now that we're tuned exactly at 0 Hertz, it would essentially be DC going into the PC speaker. So I want to move that up to a pleasant tone of 600 Hertz, which is I like for CW work. So I'm going to generate a signal source here, again at 2,500 samples per second, the same as my sample rate, and at 600 Hertz. It says cosine, but it's actually a complex sinusoid, a cosine and a sine coming out the real and imaginary parts. Minus sign, actually. Anyway, I multiply that to do a complex upconversion to plus 600 Hertz baseband if I were tuned down to 0. Then I go into this AGC. The attack and decay rate, I kind of just played around with those until I could get it to keep it from popping when I initially turn this thing on. There's no real way to figure it out, I think. At least I haven't figured it out, other than just futzing with these values. Now the reference here, notice I've got a volume knob over here which goes from 0 to 10. So the reference is the actual set point for this AGC feedback loop. So I just changed the set point from 0 to 0.05 to get the proper level before it gets into the PC speaker. And you actually have to limit the gain here too. So now I want to take that complex baseband and actually convert it to a real signal so I can listen to it. So this is done by taking the real and the imaginary parts and taking the Hilbert transforms those, then tapping off either the real or imaginary for this one or the real for that one. You can see if I take the imaginary of this and the real of that, I can add them together to get the upper sideband. If I were to reverse that and take this one and add it to that one, I would get the negative sideband, but we're only interested in upper because I've got plus 600 Hertz right here instead of negative 600 Hertz. Now that's running at 2,500 samples per second, so I'm going to do a rational resampler. So multiply it by 48,000 and decimate it by 25,000. That's going to give me the proper 48,000 samples per second to run into the audio sync. Right, now that I'm able to listen to the audio, what I want to do is get a power reading out of this thing, a calibrated power reading. So first thing I'll do is I'll take a calibrated signal generator and feed it into the USRP, and let's say choose a frequency of 5 megahertz and minus 70 dBm. So I'll fire the script up and figure out, see where that signal falls on my spectrogram right here, and let's say it falls at minus 60. That's a little too high. Then what I want to do is reduce the gain value right here by 10, so it pulls it back to minus 70. So it went the other direction, so I can see I've got a gain value offset of 19 right here. So that will ensure that a minus 70 dBm signal actually shows up at minus 70 dB of full scale DAC, because that's what it's referenced to on the frequency sync. So now to actually get a numerical value out of this thing, a true calculated mean power, I want to calculate the mean square power. So we'll take, and I want to do that at the filtered bandwidth right here, actually at the 2,500 Hertz bandwidth. So what I'll do is take this complex to magnitude squared, which for each sample it essentially takes the sample times its complex conjugate, which gives you the magnitude squared, and then I integrate that, which gives me mean square power. And I'm going to do a decimation and essentially an average of 500 samples. So that's going to get me down from 2,500 samples per second to approximately 5 samples per second. It doesn't need to be any faster than that because I can't read any faster than that on the screen. Then I'll take, and once I know that value, I'll take, this is linear, you know, absolute power. Then I'll take and take 10 log of that. I'm going to offset it by this value right here. So then I'll have that minus 70 dBm coming in the signal generator, and I'll see what value is displayed from my probe, and I'll offset it to get a true minus 70. Now, how's that displayed? This probe right here, this is a, you know, GNURadio is a synchronous flow, but I want to be able to asynchronously pull samples out. So I've got this probe signal block, which goes in, you know, it goes into there, and this has functions built into it. One of them is called level, and that will pull the value coming to the floating point input right there. So this variable function probe variable right here is going to call the function called level from my block, my probe block right there. So this one is going to take the level function, assign it to this value right here. Then I take in the Qt GUI label, I take and I format that value to 1 decimal, you know, 1 decimal precision. So, you know, for instance, it would be 70.1 dB. I don't have a bunch of values trailing that, and I give it a label for dBm. So now, also in here, there's a, somewhere in here, I actually set the, yes, pull rate is 5 Hertz, because again, I set this down here to a 5 Hertz. It doesn't have to be at exactly 5 Hertz. I can pull it faster than that, but it doesn't need to be pulled faster than that, because this is only going to be updated every 5 well, it's updated constantly, but I only get a decent value every 5 milliseconds, well, 200 milliseconds. Alright, so what I've done in order to check and make sure that all these calculations, the DD offset frequency and all that stuff, and LO tuning in GNURadio are correct, I've taken the 10 megahertz output from the back of the USRP X310. I'm running that through about a 40 dB attenuator and into the LFRX input. So essentially, if the LO drifts in this thing, it shouldn't make a difference because the whole system will drift, and we should still get the same number. So this was just to ensure that our calculation is correct, not that the GPSDO is aligned or anything. But anyway, you can see the band spectrum right here at 250 kilohertz, and right now it's centered at 10 megahertz. Then the 2500 hertz narrowband spectrum is set at also 10 kilohertz, and I can go through, if I want to change the band, I can do that right here. But I'll change it back to 10 and resets the spectrogram, of course. But I can also change the filter bandwidth, go from 1 kilohertz to 500, and then down to 100. And what you're seeing is the blue is the unfiltered 2500 samples per second, and the red is the filtered. So you can see that change. And I can change the volume setting that AGC, and then I can tune this thing around. You can see it's getting higher in frequency as I change the LO lower, and you can see the LO right down here change. Right now it's changing 1 hertz steps, so the DDC is able to keep that without changing any of its resolution below that. But if I change it here, you'll see these numbers change. And then the power output is minus 30 dBm, and if I change that, you'll see it drop down to minus 100 something if I'm looking at noise. So now to record this thing, I'll just take and hit this record button, and now you'll see the file name will jump up with the UTC time, the LO frequency that you'll see right here, and then the 2500 samples per second. So what I'm going to do, I'll let this thing run for 2 minutes, because that's about the time that the frequency test is going to happen for. So then I'll post-process this file in Baudline. Alright, so I fired up Baudline here, so I'm going to go ahead and open my file. We're going to choose this one right here. You can see it's the 10 megahertz one, or it's close to 10 megahertz. Go ahead and hit open, and run at 2500 samples per second. I want to turn the compression off, decompression off. 2 samples that are in quadrature, and 32-bit floats. That's what GNURadio puts out to its file sync. And go ahead and hit open, because I know it's going to work. So now we're already zoomed in, and let me bring up the frequency display calculation algorithm and then the windowing. I'm choosing a square window. You can see you can go through different window types right here, but since I already have a really good signal noise ratio, I'm not worried about side lobe levels. The wind-in will allow you to have better side lobe resolution with, I think, some trade-off in frequency resolution. So since I have a good SNR, I'm just going to turn the windowing off. And then I've set the transform size to 524,000 approximately. Since I ran for 180 seconds, 2 minutes at 2,500 samples per second, that comes out to 450,000 samples. So that transform FFT size is a little bit larger than my sample size. So it's going to do some, should do some zero padding at the beginning and the end. But what Baudline is doing is it's going to grab those 500-something thousand samples, do the FFT, and then it's going to slide along by one sample, do the FFT again, and then keep on going. So you're getting this continuous FFT moved across your samples. So now if I bring up this, again, the frequency display, I'm not sure actually how this works. If you go to the Baudline website, they call the name, but it doesn't go into detail. But you can see it's got very good resolution down past the microhertz. So what I'm going to do is slide this thing along until I peak it out, and it peaks out about right there, about right there, 19.106 microhertz approximately. So what I'm going to do is take that value, and that's the value in hertz, of course, that's offset from our local oscillator. So you're going to take this value that we read up here and add it to the LO value. And when you do that, it comes out to almost 10 megahertz. It's 1.16 millihertz below 10 megahertz. So that is approximately 116 parts per trillion error. And if you were to multiply it by the 116 parts per trillion, you get it back right up to exactly 10 megahertz. But so that's what 11 times 10 to the negative 11th error. Now my GPS disciplined oscillator channel invariance is 1e to the minus 11th, so I'm getting about 10 times as much error here as my GPSDO could give. But again, that's really not an issue because, again, we're feeding back that 10 megahertz signal, so any kind of drift in the GPSDO would not show up here. Now, it could show up in the difference in the sample rate, because I'm not exactly sampling at 200 megasamples per second, sampling a little bit faster, then that's going to show up as a frequency change in here. So it should show up there. But anyway, you can see it's looking very accurate. And in the ARRL frequency measurement test, they only list the values of the frequency measurement down to a 10 millihertz range. They don't give you below that. So as long as I can stay within 10 millihertz, I should be okay. So again, I'm not sure whether that error is due to error in the sample rate, whether it's something in the way Baudline calculates it. It could be in a clock synthesis in the USRP also, because it takes that 10 megahertz reference and he uses that to discipline a 96 megahertz TCXO that's on board, and that 96 megahertz TCXO goes to a clock synthesizer IC, which generates a 200 megahertz A to D and DAC clock. And that is actually programmable. You can change that. It doesn't have to be 200 megahertz, but it could be an error in there. I think it's all integer end synthesis, so there shouldn't be. But I'm still not sure what's creeping in. But it's acceptable, I think, for this frequency measurement test. Now, what I've also done, I've recorded 2 minutes of the 2.5 megahertz WWV. And using the same settings in Baudline as we did for the 10 megahertz, if I look, I'm about 6.8 millihertz below our DDC frequency, which is 7.6 millihertz above the true frequency of 2.5 megahertz. So if you do that calculation, what I'm measuring is 837 microhertz above the true 2.5 megahertz. So again, we're looking pretty good, and you can see we got a pretty good signal noise ratio down there. Okay, this is the ARRL frequency test. It's it's November 12th, 9:03 Central Time, which is what, 3:03 UTC time. Anyway, we're measuring at doing the frequency test, measuring at 7055.413 kilohertz approximately. Here's a signals being broadcasted right here. I've tuned into this narrow 100 hertz band, even though I'm digitizing the whole 2 kilohertz swath right here. And this is my wideband display and my fine frequency tuning. There you can see the very strong signal right here, and it's fading in and out, so this is going to be real tough to extract the frequency. But you can see my LO is set to 7055413.999925 hertz. I can get about I think around 60 microhertz tuning resolution out of this, and you can see it's being saved to the file name. This 2 kilohertz band is being saved. I've got the computer time right here, seconds UTC, then the LO frequency down to the microhertz, and then my sample rate 2500 samples per second. So this is going to record for about 3 minutes, and then we're going to switch on down, change the band right here down to 80 meters. I think comes up next, and about 15 minutes past the hour, and then it's going to go down to 160 meters, I think, at a half hour past the hour. But this is what we're recording, and it's going to be, you can see the fading's really bad, so we'll see what it looks like in Baudline when it's finished. Alright, we're back on down at 80 meters now at 3598 kilohertz, and now you can see there's a really nice signal now compared to 40 meters. So I've switched down to 100 hertz. I can narrow out to 500 hertz, and you'll see the red change right here, or go all the way out to kilohertz. But we don't need that. We're going to go down to 100, and then you can actually see the signal in the spectrogram too. Pretty strong, right there. So I've centered it right here. My LO is this frequency right here. My receive power was up to minus 75 dBm. Well, minus 70 right here, you can see. This is an average power taken every 10 seconds. And so when the announcement is done at 18 after the hour, I'll hit this record button and record the 2-minute CW signal. This won't require any further processing since there's no interferes. You can see I've only tuned up 200 hertz in frequency from the 3598. You know, that they said it was going to be broadcast at. And probably about 20 seconds till we get the CW tone, or a constant tone, to measure. I probably could be recording this now, but I'm not going to bother since it's not a constant tone. That's W1AW that you hear. ARRL station. There we go. Now I'm recording. You can see again the timestamp and the exact low frequency down to microhertz and samples per second. So this is going to run for 2 minutes. We can really see the fading too. You know, it's almost off the scale up here. And a minus 70, but looking at the power down here, you can see it fade in and out. Over here you can see the nice strong signal, and well, there it goes. Nice strong signal in the wide constant frequency, the wideband 250 kilohertz channel. And here we are right here. You can see it in the spectrogram. No, I can't change once this file's being written. I can't change any of these LOs, or it won't record the new frequency and I'd lose it. And the key down, the key is going to go up here in probably about 30 seconds, because it's almost 20 minutes after the hour was going from 18 after to 20 after. And we'll stop the recording after that. See a lot of other activity in the band, 80 meter band, and that's it, it's done. So now I can move on down to 160 meters. You can see it's gone ahead and retuned and centered me up for 1840, but I'm going to go ahead and return that course tuner to 0 hertz. And we'll wait now until 30 minutes past the hour for the announcement and the tone. Alright, here we're down on 160 meters now. You can hear the call up. It's actually at about 1838 megahertz. Going to narrow it down to 500. You can see we're still centered. And I'll go ahead and narrow it down to 100 hertz. And still centered nicely so we can hear it. So, yeah, this thing was supposed to come up at 1840, so you can see it's actually at 375. But again, I'm recording this whole band, so it doesn't matter as long as I know the LO exactly. So again, we'll wait until the announcement is done and I'll start recording. The reason why I don't want to record the announcement is because it's AM modulated, so we're going to get some sidebands in there that are probably going to be at a few hertz away from the desired center frequency due to the AM, quasi-AM modulation of the CW. So we'd just do a single tone and it'll be easier to measure an average. We're not as strong. We're at, peaking out about minus 85. We used to be up at minus 70 at the 80 meter band, but still much nicer than it was at the 40 meter band. Probably got about 2 minutes to go until the constant key down. Let's see if we can find it down here in the spectrogram. It should be at about 1838, 1837, so 1810, 20, 30, 40 right here. Oh, right there actually. Yeah, right there. You can see the individual CW pulses right there. only got about 30 seconds. You seem to be going a little long on the announcement. It's already 34 past the hour. It's supposed to be done at 33. There we go. That's recording. Again, you see the system time in seconds, UTC. I think that's seconds since January 1st, 1970, I think. And then, of course, the LO frequency and the sample rate. And let it record for 2 minutes. Big fade there. that's it. Maybe, let's see. Yep, that's it. So we've got all 3 files now for 40, 80, and 160 meters, and now it's time to post-process them. Now I've opened up the recording, the 2-minute recording for the 80 meter signal, which had the best signal noise ratio of the 3. Again, using the same settings. Scrolling through this thing, you can see a nice peak about right there in the spectrum, the lower half of the screen. What I'm going to do is go ahead and scroll through this thing. We're going to pick the peak value. And this is actually, I did this before I did this recording, but the value I picked was going to be 54.443291, which is going to be about right, 443, about right in there. Anyway, if you take that offset of the 54 odd hertz and add it to the LO frequency that we have right here, you'll end up with the value that I'm not going to say. I'll show it to you here when we get on the website, and we'll see how much error it came up with. All right, now I've loaded up the file for the 160 meter, and you can see how, as I scroll down through this thing, you look at the peak in the spectrum, that it's moving around. I'm not sure whether that's Doppler or whether it's something the way I've got the FFT link set, but again, I chose a value in the about middle right there, and you can see the signal noise isn't nearly as good as the 80 meter was. And finally, this is the 40 meter signal. You can see it's a real mess. There's only about it looks to be about 10 dB, and as you scroll across this thing, you see a little bit of there really is no peak. So I took a value right in the center here, about 21.82, right there, 21.821 hertz offset, which we'd add to there to get the true frequency. All right, here I've gone to the FMT website and entered my call sign and QTH state, but here I've entered the 3 frequencies that I calculated from Baudline, and then detailed the method in which I did it. Essentially, the active loop antenna through an AM notch filter, the USRP with decimation by GNURadio, and then filtering, and then into Baudline to do the FFT, and then detailed the signals that said 80 meters was strong with a 40 dB SNR and 100 hertz bandwidth, and 160 meters had 30 with fades down to 20, and 40 was about 10 with fades to 0 or below. Lots of QRM. There's a Canadian sideband net happening, maybe kilohertz above that was bleeding onto it. I didn't realize that Canadians could do sideband on a CW portion of the band, but I guess that's only US who restricts that. All right, well, it's 2 days after the test, 2 evenings after the test, and here are the final results. I entered the results last night. You can see I came in right here below 1 hertz for all bands, 160, 80, and 40. And here's the true frequencies right up here. And here's my call sign right there, KD4HSO. So let's scroll down and see what I actually got. See what the error was. Here I am right here. So 80 meters had the best signal noise, but you can see I was 100 millihertz low right there. 160 meters, I was 70 millihertz low. And at 40 meters, which was, it doesn't surprise me, I was a whopping 700 millihertz low. So that didn't seem to be much signal to work with, at least not trying to find the peak in the spectrum. I was surprised that I didn't get a better number right here on 80 meters. You can see that they're all low, even though I know that there was a 116 part per trillion error that I could correct it for. That doesn't get me anywhere near the correction factor to get these numbers, so I'm not sure exactly what's going on, but I still came in under a hertz, so I'd like to have done better. You look at this guy's results right up here, he's done very well, and he's actually using all homebrew analog equipment. It's an interesting read up here. Here's the 2014 November results. You want to go out there and scroll through some of this stuff, but some pretty impressive results by some of these guys. Anyway, it was an interesting test. I've been wanting to do this for about a year and haven't gotten around to it, but now I finally have. So I think I'm going to try it next year and try to track down where all these other sources of errors are, and also try to use Baudline more and figure out exactly the best method to use it. You know, since I was picking that transform size that was larger than my sample set, you know, do I pick a bigger transform size and try to get more averaging with zero padding? But that really doesn't add any frequency resolution. It just spreads the energy into smaller bins, but doesn't really gain you anything. So I'm not sure what the best settings are going to be, and then exactly how to handle the windowing also. And then I also want to figure out what the errors could be within the USRP's clock synthesizer and other things, and try to track all that down. Anyway, hope you enjoyed the video.